Okay. Hi everyone. Sorry to keep you waiting. Um, so I would like to start the next version of or next edition of neural networks for NLP. Are did anyone have any Did anyone have any questions about the material last time or class format or stuff like that? No. So I got a couple questions on Piazza, so I encourage you to ask questions there and more, etc. Um, so anyway, this time I'm going to talk a bit about a simple exercise which is predicting the next word in a sentence. This is also known as language modeling. I'm going to talk about language modeling itself, but I'm also going to use this as a general way to introduce a lot of the tricks that we use for training neural networks. And I think if you've used neural networks before, a lot of these will be familiar to you, but you might not be using all of them. So you can, it will be useful. If you haven't used neural networks before, you can use this as a recipe of things that you should be doing when you train your neural networks for NLP. So this is the thing I showed last time. So are these sentences okay? We have a bunch of different sentences. And maybe the first one and the last one are good English, and the others are not. And so basically, language modeling is the task of determining this by calculating the probability of a sentence. And because I assume everybody here has taken an NLP class before, you know this formula where basically we can calculate the probability of a sentence X by multiplying the probability of all the words in the sentence like this, according to the chain rule. And so that's the next word, and these are the contexts that we're making our prediction on. So the big problem here is how do we predict this word-by-word probability? How do we predict the next word? And if we can do this, we can calculate the probability of all of our sentences. So this is just review from your previous NLP class, just in case people have not seen this before. But the way we did this most of the time up until a few years ago was basically with count-based language models, including mostly Ngram models. So the way we do this is first, we generally make an approximation. So instead of calculating using the context all the way back to the beginning of the sentence, we use the previous n-1 words. So if it's I am giving blank, then if we're using a trigram model, we'll use only the past two words, etc., which you should already know. And then the way we calculate this is we count up the number of times we've seen giving and then we count up the number of times we've seen giving something, and use this to calculate the probability of something. And then we do stuff like adding smoothing to deal with zero counts. So we might interpolate the current probability estimate with the current maximum likelihood probability estimate with one of lower order. And then we do more fancy things like modified Kneser-Ney smoothing, where we also modify the counts of the maximum likelihood estimates of the lower order counts, etc. So this is all familiar to people, right? Okay, so we're not going to do this. We're going to do something else. But first I'll talk about evaluation. So evaluation, there's a number of ways we evaluate language models. You can start out with log likelihood. So you take the log likelihood of all of the words in your test corpus. So calligraphy E test is your test corpus. And then E, uppercase E, is a sentence in it. Sorry, this was X before, but I'm a machine translation person, and we write our target sentences as E, so forgive me if I switched notation here. We also often calculate per word log likelihood, so this is good because it normalizes over different size corpora, and you can roughly compare corpora with different numbers of words. You can also call this per word entropy, in which case, instead of taking the log of E, we take log 2 and we do the minus. So entropy, what is the reason why we would take log 2 instead of log E?
Bits.
Yeah, exactly. So it's the number of bits that you would need to compress the thing using this language model if you were using something nice like arithmetic coding or something like that. And then perplexity. So this is equal to 2 to the entropy, or 2 to the negative word log likelihood, or e to the negative word log likelihood. And what is the definition of perplexity? Or like what is the interpretation of perplexity? Yeah, that's pretty. It's how surprised you are, but also like more accurately.
How many different branches for words are possible?
Right. Yeah, basically, it's more or less the average number of times you would have to guess to get the correct answer. So if you guess from your top probability one and walk down the probabilities, you would have an average of n guesses before you got the correct answer. That might not be completely correct in all cases, but it's a pretty good approximation. Another reason why people use this is it looks bigger than entropy, so it's easy to publish papers if you have perplexity gains, but we'll ignore that for now. So what can we do with language models? We can do a variety of things. We can score sentences. So this is the more practical of the two things if we're just talking about language models. So we have a speech recognition system that outputs 10 hypotheses, and we need to know which one looks best, or a machine translation system. And we use this to score them, score the hypotheses based on how good they look. Or if you want to play around with language models and see what they think about language, then you can also generate sentences. So while you didn't choose the end of sentence symbol, you calculate the probability, you sample a new word from the probability distribution, and you continue to do this, and you can get random sentences generated. So this time we'll try both of these, but we'll try it using neural networks. And n-gram models have problems. They're actually very, very good. And they were very, very hard to beat for a long time as a baseline, but they do have their problems. And they cannot. One of them is that they can't share strength among similar words. So if we have she bought a car, she purchased a car, she bought a bicycle, she purchased a bicycle. Car and bicycle mean kind of the same thing. Bought and purchased mean kind of the same thing, but you have no concept of this. So if you've never seen purchased a bicycle, then you would not get any gain from your model based on seeing the other ones. You cannot condition on context with intervening words. So Dr. something Smith is a pretty common n-gram, basically. So Dr. with something in the middle and then Smith is a good indication that this is correct. But actually, if you get a rather unusual name like Gertrude or something like that, you would just fall back to your unigram probability and lose all information there. They also cannot handle long distance dependencies. So if you have for tennis class, you wanted to buy his own something, you know it's probably racket or tennis balls or uniform or something like that. On the other hand, for programming class, he wanted to buy his own racket, you'd be wondering what he was doing in programming class. So each of these has solutions, a battery of solutions in count-based models. So we have class-based language models, which allow you to share information among classes. We have skip-gram language models. So before skip-gram from word to vec, which some people might have heard of, there was another meaning of skip-gram, which was you skip over a single word and predict using the second to previous word. So we had these. And for long distance dependencies, there was a whole battery of solutions called cache models, where you try to repeat the same word over and over again. Trigger models, where you try to repeat corresponding words. Topic models, syntactic models, etc. And there's a paper, which actually I think I forgot to add to the references, called A Bit of Progress in Language Modeling. So this is actually a pun. It's literally a bit of progress in language modeling when you measure according to entropy. So it was by a guy named Joshua Goodman, and he basically took a regular n-gram language model and threw in all the methods that they knew how to use at that time. And it was quite a bit of work, and you got a bit of improvement in entropy. A bit of improvement in entropy is not bad. It's halving your perplexity. But still, it was quite a lot of work to do something like that. So one of the good things about neural networks is they give us all of these things with a model that's much simpler than the very difficult model that Joshua Goodman made 10 years ago, 20 years ago maybe, I don't know. So the first thing I'm going to talk about is featurized models. So neural models are featurized models. Like all neural models are basically featurized models. They calculate features, then based on the features, they make predictions of the words. But first I'm going to talk about a simple variant of this called featurized log linear models, which were actually invented by Roni Rosenfeld, who's in the MLD here. So I should probably also add his paper to the references in case he looks at my class website. Just realized I forgot that one too. But anyway, so these featurized models are basically what you do is you calculate features of context. Based on the features, you calculate probabilities. And you optimize the feature weights using gradient descent or some other algorithm. So if we have an example, this is kind of my running example of language modeling. We have the words giving a, and we want to predict the next example here. We have the words we're predicting. So these are all the words in our vocabulary. It's a big list of 30,000 words or 10,000 words or whatever. Then we have a bias for each of these words. So this bias is basically how likely the words are going to be in general. So and the are very likely normally. Talk, gift, and hat are a little bit less likely. Then how likely are they given that the previous word is a? So if the previous word is a, then suddenly the probability of and the goes way down because you don't have a or a the in your sentences unless you're explaining about language models like I just did in my previous sentence. So then we also might have a feature like how likely are they given that the second to previous word was giving. So if this is the case, things get a little bit more fuzzy. This is the skip Graham model that I talked about before. So now we're skipping one word and predicting the next one. But if it's giving and then something and then some other word, then giving something talk, giving something gift is a little bit more likely than it would be if the word was not giving. So we might be able to come up with a feature vector where it slightly increases the probability of talk and gift itself. So then we have the total score, which is the sum of all of the feature scores, or the sum of all of the scores here. And then we use this to calculate the likelihood of our sentence, or of our next word in the sentence. So gift would be 2.2, that's maybe the highest, and talk would be 1.0, etc. So then we convert the scores into probabilities by taking the exponent and normalizing, which is the softmax function that I talked about a little bit on Tuesday. And we'll be talking about almost every class until the end of the, we won't be talking about it, but we'll be using it almost every class until the end of this finishes. But basically, this is, we take these scores that we calculated, and then we exponentiate them so they're all positive. Then we normalize so they all add to 1. So basically, this turns scores into probabilities. And if we do that to our previous score vector, then maybe this gets a score of 0.44, 0.329, etc. Okay. So are there any questions so far? Is this okay? Yeah. Yeah.
Do these featurized log linear models improve over n-grams much?
If you try hard enough, yes. So they improve most when you interpolate them with n-grams, like anything else did at the time. So until basically the RNN language model, which we'll talk about later, came out, there were very few things that outright beat n-grams. Right. There were lots of things that helped a little when you interpolated them with n-grams, but this was another one of those things. And on the computational hardware they had then, these were actually difficult to train compared to n-grams, which is probably why people didn't use them. Yeah. Anything else? Okay, so I'll move on. We can explain this as a computation graph. It's a very, very simple computation graph. And basically what we do is we have two varieties of lookup parameters where each of these vectors is the size of the output vocabulary. So we look up something for giving in lookup 2. We look up something for A in lookup 1. We have our bias, and then we add them all together to get scores. And then we use this to take the softmax and calculate probabilities. So this looks actually extremely similar to what we had in the bag of words sentence classification on Tuesday. The only difference between this and the bag of words sentence classification is we're actually doing the positional. We're doing different features based on position of the word. So yeah, this is how we would implement this. As it's not a neural network really, because it doesn't have any nonlinearities, and usually we think of neural networks as having nonlinearities, but you can think of it as a computation graph anyway. So I've been saying lookup since the very beginning of the class. I should do a little clarification. There was also a clarification in Yoav Goldberg's book about this, about dense versus sparse vectors. So lookup essentially can be viewed as grabbing a single vector from a big matrix of word embeddings, or a big matrix of vectors representing something or other. So here is the example. We have a matrix where each column corresponds to a word, and each row corresponds to the size of the vector. In our case now, this is the size of the output vocabulary. Later it will be a different size. Then if we look up 2, we basically grab the third column if we're doing zero indexed. If we're doing something zero indexed, or the second column if we're doing something 1 indexed. But we grab a column, and this is our vector that we'll be using. There's another way you can look at this. You can also view this as multiplying by a one-hot vector. So a one-hot vector is a vector where you have 0, 0, 1, 0, 0, 0, 0, 0, 0 for the rest. So these are both mathematically absolutely equivalent. The only reason why it's maybe better to think of the first one is for computational reasons. So if you actually do a matrix multiply, this is a huge waste of time. We do the first one. And in DINET and other neural network libraries, usually they have something like lookup parameters or an embedding, or embeddings, and those usually use the first approach. Yeah?
If the library we're using supports sparse matrices, then it should be able to do this really fast, right? Because essentially that's just a lookup.
Yes, but it will still be slower than doing the first one, I think, because a sparse matrix is more generalized, but I think it would be reasonably fast. Yeah. Another reason, which I'm going to talk about a little bit later, is that when you update the gradient, when you calculate the gradients and do update of parameters, when you do parameter update, if you do it the first way, you can keep track of the ones that you used. It's easier to keep track of the ones that you used and only update the ones that are on that were used. And that's a huge gain on CPU. It's not a very big gain on GPU, but Dynet does this natively by default on CPU. So that's another thing that can help a lot if you have a big embedding table. Yeah, so anything else? Yeah. Oh, okay. So lookup, you're talking about the previous slide, right? Here? Yeah, so basically, we are defining two different sets of parameters. So each set of parameters, we can view this as a matrix where the number of rows is the size of the vocabulary and the number of columns is also the size of the vocabulary. And if we only had one of them, regardless of which position giving and A came in, you would get the same values. But if we have two different separate ones, the values will be different based on whether giving is the second to previous word or the previous word. So that's the idea there.
So it's basically a tensor lookup with one of the dimensions represents the index of the position of the word in the n graph.
You could view it that way also. Yep. Any other questions? No? Okay. So I already skipped to the next one. So when we're training a model, to train, we calculate a loss function. So a loss function is basically a measure of how bad our previous predictions are. So when we train our model, we train it to reduce the loss function. So I mentioned the words stochastic gradient descent before is how we're training our model. And basically, the reason why it's stochastic gradient descent is we want to descend to a lower point in our loss function. So this will generally or almost always be a positive number that we want to reduce to 0 as we do training, or reduce to as close to 0 as possible. And then the most common loss function for a probabilistic model is negative log likelihood. So basically, what negative log likelihood is if element 3 or 0 index 2 is the correct answer, we grab the third example here, we take the negative log, and this gives us 1.112. And then we will be calculating our gradients in order to reduce this to be a lower value. So yeah, we do parameter update. We calculate the derivatives using backpropagation, like I talked about last time. And we do a simple update like this. Or we can do a simple update like this. So this is theta will be modified by dl d theta, but multiplied by alpha, which is our learning rate. And adjusting your learning rate is super important. If you have a too big learning rate, training explodes. If you have a too small learning rate, training takes forever or doesn't ever get anywhere useful. So if you're just using this simple stochastic gradient descent, it's very important to pick your initial learning rate. So that's that. This is kind of all basics that if you've used neural networks before, you probably know already, but it's, if you haven't used them very much before, it's important. Also, another thing, this kind of goes along with count-based language models, but it's a little bit more important when you're talking about neural language models. So you need to choose a vocabulary of the things that you're going to be predicting. And also the things that you're going to be using as input to your model, like word embeddings. So we have a concept of unknown words. And basically, the reason why these unknown words are necessary is, number one, we don't have all the words in the world in our training data. So if we get a new sentence and it has a word that we've never seen in the training data, we need to treat it appropriately. The second reason, and this is exclusive, or mostly exclusively a problem of neural models, which is that large vocabularies require more memory and computation time to do. So this is particularly important in the softmax layer, because in the softmax layer we do this big matrix multiply, and that matrix multiply we can't really avoid unless we do something tricky. I'm going to, or more accurately Taylor, is going to talk about the tricky things we do next Thursday, but for now just assume that the softmax takes a lot of time to calculate. And then there are a number of common ways to choose the number of unknown words. So basically we either do a frequency threshold where we make all unknown words less than or equal to, or all words less than or equal to one unknown in the training data, or we can have a rank threshold where we take the top n words, which is pretty common. I'm going to give some examples on Penn Treebank data later. In the Penn Treebank, the standard Penn Treebank version that people use has the top 10,000 words be in the vocabulary and everything else be unknown. Just as a quick aside, usually as our unknown word token, we do this. We put a couple brackets on either side of UNK. One time in my code, or the code that some people here were also developing, we had it as uppercase UNK, but this makes University of Nebraska at Kearney an unknown word. So for the people in Nebraska, please make sure you put brackets around it like this, so they don't get their college unked. Okay, so one really, really important thing when you're talking about language models is when you do evaluation, you have to use the same vocabulary for all the models you're evaluating, or with one small qualification. So the vocabulary must be the same over the models you compare, or more accurately, all of the models must be able to generate the test set. So what this means is it's okay if they can generate more than the test set, but it's not okay if they can generate less than the test set. So if you have one model with a vocabulary like this, and you have one model with a vocabulary like this, which is a subset, but for some reason the entire test set is covered by this subset, then that's okay. But it's not okay if you can't generate the stuff in the test set. So for example, you could compare a model that had some sort of character-based generation component to a word-based model, but they would just have to, you'd have to make sure, but you couldn't really compare a word-based model to a character-based model unless the word-based model can generate all of the words in the test set appropriately. So I have an example, or were there any questions about that so far? Yeah.
What happens if you generate less than the test set and try to compare?
What happens then, so actually people did end up doing this previously. And what happens is the model with the smaller vocabulary will have an unfair advantage. And the reason why is, let's say you have something that is predicting A, B, and UNC. And you have another thing that's predicting A, B, C, D, and UNC. And these have a uniform distribution. If they have a uniform distribution, this model will have a perplexity of 3, and this model will have a perplexity of 5. So it's starting out with a disadvantage. It might still win in the long run for whatever reason, but basically it's unfair to this model. Yeah.
Does the unknown word means the words that not included in the vocabulary set?
It means any word other than the words included in the vocabulary set, yeah. Yeah.
But isn't it possible that two models with different
Uh-huh.
The comparison is still unfair because one of them has a larger vocabulary.
Not if you're evaluating on that test set, then that's okay.
Because it has a
Yeah.
larger vocabulary, wouldn't the probabilities of the words in the test set be lower?
Yeah, I think what would be unfair is to look at your test set when you were making your vocabulary. But if you're not looking at your test set when you're making your vocabulary, I think in reality, this will never happen. If you are, if you're using a normal way of creating a language model. So in general, you just match the vocabulary for your word-based models when you're comparing them. The only reason why I said that is because if you want to compare like word and word plus character-based models, sometimes you might want to do that. And if that's the case, then actually the word plus character-based model has a disadvantage because it has a larger vocabulary, but it also has an advantage because it can look at the subword regularities, and it might be able to give rare words a higher probability based on like what their shape looks like. So I think when you're just comparing two word-based models, you just compare ones with the same vocabulary, usually. Yeah?
To add to that, you will normalize by the size of the test set. So when you normalize, then you can compare two texts. So when you look at the probabilities is normalized by the size of the vocabulary. Exactly. No, by the size of the test set. If it is normalized by the size of the test set, then the two probabilities are equal. Yes. So the probability in the normalization will be of the vocabulary, or the test set, or the test set.
So yeah, maybe we can talk about this afterwards. But so here is a coding example, which is still very, very small. So this is, if we want, this is a simple log linear language model. So the first thing we do is we specify the length of the n-grams that we want to cover. So in this case, I'm using a trigram model. So it will look at the previous two words as it's doing its generation. So then we go down a little bit over here. And this is the boilerplate vocabulary reading code that we were using before. One thing I should mention is now we don't have tags, so we're not reading in tags. We're just reading in words. I can show you what the data looks like. So if you have ever worked on language modeling before, this data will look very, very familiar to you, because this is the very standard language modeling data set, the Penn Tree Bank data set, which you've probably seen in a lot of things. This was made. The Penn Tree Bank is a big thing of parse trees that was made a long time ago for syntactic analysis. This is a pre-processed version that was created by Tomas Mikolov, who made the RNN-LM. But now it's kind of, a lot of people use this. But you'll notice it already has words unced in here. So you don't have to go and do the unking yourself. Normally, when you do language modeling experiments, you have to do it yourself. So for the sake of simplicity, I'm skipping that part, but this is actually quite important. So then we go down, we read our data and have our vocabulary. We start up DINET, and then the next thing we do is we define the model. So here what we're doing is we're defining lookup parameters, but we're defining a list of lookup parameters of size n. So as I said before, we had lookup 1 and lookup 2. This is basically lookup 1 and lookup 2 here. Then we have the thing to calculate the loss function for the entire sentence here. we renew the computation graph because that's what we do. Then we create a history. So this history is the beginning of sentence symbol. And this is what we will use to predict the next word. So when we predict the first word in the sentence, our history is basically beginning of sentence, beginning of sentence. Then we have a list of losses. Then for each word in the sentence, we calculate the score of its history. This is a function that I defined above, and I'll show you later. We append this pick neg log softmax. So this is our way of calculating the negative log probability. And then we modify the history by removing the previous word and adding the word that we just predicted. So simple enough, I think. Then we add all of our losses together, and then we return this. Then if we look up here, we're going to have a number of vectors that we add together. If you remember, we added together the bias vector and then the feature vectors for all of the things. So then we zip through the words and the lookup tables. So the first word will go to the lookup table number 1. The second word will go to the lookup table number 2. And we add this. And we add this to our score vectors. Then we add together all our score vectors. So this is just the, if you go back here, this is just the computation graph that I showed you all the way up. Sorry, that's farther up than I thought. All the way up here. So add this at the beginning, then add this and add this. So that's all we need to do. Then the rest of our evaluation loop is down here. This is very similar to the one that I showed you before. But this time, instead of evaluating the accuracy on the dev set, we just evaluate the log likelihood or perplexity on the dev set. So that's all we do. And then if we want, we can try to run this. And you can try to run this as well on your local environment if you'd like. And we can see that training for this is much slower than the one that we had before. But it will probably show up in a little bit because it's churning through 5,000 sentences or something like that. So I'll let that running as I continue explanation or take questions. Are there any questions about this related stuff? Or? No? Okay. Cool. So I will move on. I'll move on, and if you're interested, you can take a look at the code there. Okay. So now I think it's worth going back and thinking of what problems of our previous model that we've solved now. So if you think about it, what I talked about before was we can't share strength among similar words. We cannot condition on intervening words, and we cannot handle long distance dependencies. So the model we have now, has it solved the first problem? Anybody? Who says yes? Who says no? It's a pretty good turnout, and then there's like 70% of people who aren't quite sure. So the answer here is no, it hasn't done this. And the reason why it hasn't done this is because we're still remembering correspondences between a single word in the context and a single word in the output. So we don't have any concept of sharing yet, but that's what we'll get to in a little bit. What about the second one? Can it condition on the context of intervening words? Who says yes? Who says no? Okay, this time 100% accuracy. So yeah, we did solve this one, and that is we solved it because we're directly using the previous context, or the second to previous context. And then the final one, I don't know if I even need to ask this, but who thinks that we've solved long distance context? Who thinks that we haven't? Okay, yeah. So the reason why we haven't is because we're still only using the two previous words. We're not using any information about the words there before. Yeah. So let's move on to the next one. So we'll move beyond linear models because that's what we do in this course. So linear models can't learn feature combinations, as I mentioned before. So some examples of something this could not handle, or this is an example of something this could not handle. So let's say we have farmers eat steak, farmers eat hay, cows eat steak, cows eat hay. So this is very much like the combination of love, not love, hate, hate, not hate that I showed from the previous time. So here, the next word is steak only if it's farmers and eat. Neither farmers itself and eat itself are not indicative of steak being correct. As you can see from the example hay, farmers eat hay, actually maybe this wasn't entirely, I've used this example several times, and I just realized that it's probably not the best example. So to give another example, it could be, let's see, farmers cultivate hay, or something like that. So it would have to be farmers and cultivate in order for hay to be correct. That's actually also not the best example in contrast. So sorry, I'll fix the slides here. But anyway, there are these features where two things in the context need to be correct in order for your prediction to be accurate. And linear models cannot learn these model combinations. So what can we do? One thing that we could do is we can add combinations as features, as individual features. So what we do is we remember another single vector for farmers eat, cows eat, farmers eat, cows eat, farmers cultivate. And so all previous bigrams will get a feature vector of their own. And if that's the case, you could remember things like this and solve this problem. But the problem here is this would give you a feature space explosion. So now instead of having features the size of your vocabulary times the size of your vocabulary, it would be size of vocabulary times size of vocabulary times size of vocabulary. And that's very quickly going to become unmanageable, both from a computational and learning perspective. So, of course, we use neural networks instead. So neural language models, what neural language models look like is this. We have giving A, we do a lookup, we do another lookup, and this time we actually only have one lookup. We don't have lookup 1 and lookup 2, and I will explain why in a moment. Then we run this through a neural network layer, which is an affine transform, or in other words, multiply by a matrix, add a vector, and you run it through a nonlinearity. And then we multiply this by a matrix, a weight matrix. We add a bias, and we get scores. and then we turn the scores into probabilities like we always do. Oops, and my animation is broken, but so one of the really good things about this framework is it basically solves our problems of not being able to share strength among similar things. And it does it in a number of ways that are very useful. So I have purple, blue, and red here. So the red example here, for each of the words in our context we have giving here. And the words in the context basically get their own vector. And if the vectors are similar, when these words are used in the context, they will have a similar effect on the output. So for example, the vectors of in the might be very similar here, which means that things that follow and the will be given similar probabilities. Also, maybe farmers and ranchers might get a similar vector, or cows and cattle might get a similar vector or something like that. Also similarly, in our softmax, basically, when we do a matrix multiply before our softmax, each row in this weight vector corresponds to a word in the output vocabulary. These rows in the matrix, because each word corresponds to something in the output vocabulary, you can basically view them as word embeddings on the output side. So these are vectors representing words on the output side. And if these vectors are similar for certain words, those words will be likely to appear in the same context. So again, maybe farmers and ranchers would have similar vectors here, etc. Then the final place where these models can share strength is in the contexts here. So basically what this tanh layer is doing is it's taking all the words in your input, it's combining them together into a smaller number of basically contexts, pieces of information about the context. And these could contain things like combination features, like farmers eat, ranchers eat, farmers consume, ranchers consume, might all correspond to a single node in this vector or some small combination of nodes in this vector. And because of that, it can learn combination features that also generalize across words as well. So while this model is relatively simple, it's a very powerful way to basically do the things that we would expect from a class-based language model or whatever else. Yes, so in a way, these neural models can basically solve the problems of handling things with similar words, and they can also do things like similar contexts, even if the words themselves are a little bit different. So these are simple and great. So I have some code here. I won't actually run this code. You can see this is still processing. This was a lot faster when I wasn't recording video, so the video is killing my training again. But anyway, so yeah, just to look at the code very briefly, we can see this and open. Actually, I'll close this. This is again very similar to our this is very similar to our code from our log linear model with a few changes. Basically, the only changes here are now we have 2 extra parameters. We have the parameters which are the embedding size, so this is the size of the word embeddings. And then we also have the hidden layer size. And here I just set them both to 128 because it made training reasonably fast. You could probably tune these better. Oh, by the way, do people know why I always use 128 or 256 or something like that?
Just for parallel processing, it's easier with it's power of 2.
Yeah. So for parallel, the answer was for parallel processing, it's easier if it's a power of 2. And GPUs especially have 64 threads or 128 threads or something like that. So they really like powers of 2 and will do the most efficient on those. So it's not just because I like binary numbers. It actually has a reason. So here we can look very quickly. Basically, now we have a word embedding vector here. We take in words in the vocabulary, and then we have an embedding size here. Then we have a matrix multiply and add a bias vector before this. And the matrix, because we're concatenating the embeddings together, we have the input be n times the embedding size. Then we also have a softmax, which takes in the hidden layer and outputs things. And then down here on lines 44 through 54, this is our whole thing where we look up the word embeddings, we concatenate them together. We calculate a hidden layer by doing an affine transform and a tanh, and then we do another affine transform and return the scores here. And then everything else is the same within this file. So everything else, it's the same between linear models and neural network models. So I won't run this in the interest of time. You can see my other log linear model that was running is now getting, after the first iteration, it's getting a perplexity of 373. Does anybody know what perplexity should be on the pen tree bank? No? 60? Yeah, so 60 is if you try really, really hard. The standard Kneserne n-gram language model got 140 on the pen tree bank, which is kind of funny because if you remember, Joshua Goodman's paper was a bit of progress in language modeling. And a bit of progress is equal to having your perplexity. So you take the Kneserne language model, which was 140, and the Joshua Goodman paper got a bit of progress, so that's probably about 70. And now we have LSTMs, which also give us about 72 to 60 to 72. So now we similarly have a bit of progress, or maybe a little bit more than a bit of progress in language modeling as well. So it'd be interesting to go back and try all the things that he did back then and see and see how competitive it was with the LSTM language models. But that's a lot of work. So if you like doing lots of work, go ahead and do it. I think it'd be interesting. Okay, so let's go back to the slides. And that's it for introducing the model. I have one additional thing. This is not a thing that everybody does, but it's super simple and potentially useful for people. So I thought I'd introduce it. But recently, a lot of people have been sharing the input and output embeddings, and what this means is basically in language models the weight matrix before the softmax is equal to the number of or the rows are equal to the number of words. So instead of having separate parameters for the input, we can also just pick a row from that softmax matrix. And the nice thing about this is the softmax matrix it actually has a lot of parameters in it, so this can have the size of our model. And it also makes learning easier if we assume that the words on the input side and the words in the output side should look approximately the same. So I know a few people who have gotten good results with this, and a few papers have also reported that as well. So if you want a simple programming exercise based on the stuff we did in the class today, you could try implementing this in the LM example code. Yeah, so what you would do is you would delete the input embeddings and instead pick a row from the softmax matrix. Okay, so I'll talk about training tricks relatively quickly. So training tricks, basically, there's a bunch of little things that make a big difference when you're training neural networks. The first one is shuffling the training data. This was actually already implemented in my previous example. But what we do is basically before every iteration, we shuffle the order of the examples that we're training over. And the reason why is because we're using stochastic gradient methods, which means we step through the data one by one. So what if we one by one and do parameter updates? So what if we have the sentence, I love this sentence so much at the end of the training data 50 times. Like we literally concatenate this to the end of our Pentree bank training data. And then we aren't shuffling the data. What happens is we get a language model that really loves the sentence, I love this sentence so much. So it will give a very high probability to this sentence, and it will give a low probability to almost everything else. And the way we solve this is just by randomly shuffling the data. Sorry, not at each time step, at each iteration through the data. And actually, theoretically, for stochastic gradient methods, what we assume is we're randomly picking data every time. So this is kind of an approximation to that, but it's a good one. So there's also other options for optimizers. You probably heard about a lot of these in papers if you've worked with neural nets. There's SGD with momentum. So the idea here is that SGD basically is taking a step in the direction of the gradient every time. And then it's, because it's taking a step in the direction of the gradient every time, if the gradient changes a lot, you get a lot of random steps and training is kind of unstable. So momentum, basically you remember the gradients from the past time steps to prevent sudden changes. Adigrad is a method that basically adapts the learning rate to reduce learning rates for frequently updated parameters. As an intuitive example of that for this neural language model, if you think about it, parameters are only updated if that particular word, parameters for the lookup anyway, are only updated if that particular word appeared in that sentence. So if you have a word that appears 5,000 times or 10,000 times in your training corpus, it will be updated much, much more, or many, many more times than one with only 5 occurrences. So what Adigrad does is when it sees one of those rare words, it takes a big step in parameter space. When it sees one of the frequent words, it takes a small step in the parameter space. So that kind of fixes that problem and lets you train all the parameters well. However, Adigrad has a couple problems. One of the problems is it monotonically decreases the learning rate, so it tends to get stuck when you're training. So there's a bunch of other methods that try to fix this. The most popular one is called Atom. It's like Adigrad, but it keeps a running average of momentum and gradient variance, etc. Yeah, many others. There's a reference on the webpage of a very nice blog post that basically explains about all of these in detail, so you can go there and look at all the formulas and explanation, etc. Another important thing to do is early stopping and or learning rate decay. So basically, because neural nets have tons of parameters, eventually they will overfit our data. They will get a really, really good log likelihood on the training data. But they will not generalize to other things. So one way we can fix this is we monitor our performance on held out data, like a dev set, and stop training when it starts to get worse. Another thing that that helps is to reduce the learning rate in continue training. So when you get a worse log likelihood on the development set, then you divide your learning rate in half, and then you continue training after that. And smaller learning rates have a smaller tendency to overfit, and they're more stable. So this is good. This is absolutely essential if you're using SGD, like simple SGD. And for other methods, it still tends to help. Yeah, so which one to use? Atom is usually fast to converge and stable. I use it when I just want to try something out. But kind of the knowledge that a lot of people accumulated, and recently a paper came out about this, is that regular SGD tends to do very, very well in terms of generalization. So Atom will overfit much faster than SGD does. So you have a training curve where Atom basically goes down like this, and then SGD goes down like this, but eventually beats out Atom in the end on the development set. So if you have lots of time to wait and you really want your numbers to be 0.5% better, like if you want to write a paper or something like that, then using SGD is also another option. You should definitely use learning rate decay. So we tried this on machine translation. So this is actually a counter result to a lot of what people have reported before about the SGD. So actually the stuff that I said above, you should take it with a grain of salt. This is kind of the common wisdom, but this is counter to the result that we got here. So basically, we did Atom with learning rate decay, and it got better results than SGD and converged much faster as well. So I think learning rate decay is a must. Which optimizer works better with it is still, I don't know the answer to that. But this is only on machine translation, so other applications might be different.
Did you tune the learning rate on the SGD here aggressively?
The initial learning rate. So this is using learning rate decay. Oh, so to explain this graph, I'm sorry, there's points on this graph, and every point corresponds to a single learning rate, which goes to convergence, and then we lower the learning rate and restart training, basically.
In my experience, in the later SGD, sometimes when you tune it up, it will start to learn again.
So we did tune the learning rate, but we didn't tune it super aggressively. So it might be the case. There's also papers there's also a paper by Google on machine translation that just came out recently that starts with a really low learning rate, then tunes it up, and then drops it again, which is the opposite, I guess, of what you just said there. But who knows? There might be a secret learning rate. I think you should train a neural network to decide your learning rate for you. Actually, is probably the correct answer. So, but I think basically as a basic learning formula, starting with the default learning rate and then having it is a pretty good choice. And then if you want to try other things, you can as well. So another thing that really you should be using for many tasks, unless you have so much training data that you don't know what to do with it, is dropout. So most NLP tasks, or analysis tasks anyway, you don't have enough training data because it's expensive to get people to label training data for you. So in that case, they overfit very heavily. So what dropout does is it randomly zeroes out nodes in the hidden layer with a probability of p at training time only. So for example, if you have 5 nodes in your hidden layer, you would randomly drop a few of them. So one thing to note is because the number of nodes at training and test time is different, scaling is necessary. So what you do is you, for standard dropout, you scale the nodes by p at test time to reduce their scale to take into account that you're using all of them. There's also a thing called inverted dropout, which scales by this value at training time, and then you don't need to do scaling at test time. And the implementation in DINET uses inverted dropout. If you're using another toolkit, you should just be aware of which implementation it's using. So yeah, the DINET dropout function does this automatically. So you just need to use it at training time and not at test time. So I have some examples here. I'm looking at the time, and I realize we only have 10 minutes left. So all this code is on the class website, so you can go and take a look. All of these are tiny changes to the code, but will result in better results after all. Are there any questions about this? Yeah.
Why the number of nodes at training and test is different?
Oh, so the number of non-zero nodes at training and test is different. And the reason why is because we randomly zero out nodes at training time only. The reason why we don't do it at test time is basically at test time we would like to use all the information that we have. At training time, by zeroing them out at training time, you can view this as basically training a whole bunch of different models. You can view it as training an exponential number of models, and then basically ensembling them together at test time. You can read the paper for details about that, but we want to use all of the models that we have at test time, which is why we don't zero anything out of these. Anything else? No? Okay. So there's one more trick that I would like to talk about that's very useful if you want to train your models in a quick manner. This is especially important if you're training on GPU, but it's less important if you're training on CPU. It still helps a lot on CPU as well. But basically, what the idea is you want to combine together similar operations together and execute them all at once. So, for example, let's say you want to do 10. You want to add a vector of 10 elements together. You want to add 10 elements together, and you have a choice of either adding each of the elements together with a for loop, or adding a vector of elements of those 10 elements with another vector of those 10 elements. And on modern hardware, especially GPUs, but also CPUs, doing 10 operations of size 1 is much slower than doing one operation of size 10. And so what mini batching does is it combines together smaller operations into one big one. So some typical examples of this would be taking a vector of 10 elements, or let's say we have a vector of 100, or no, we have a vector of 16 elements, and we add that together 8 times or something like that, which gives us 128 values. If we dispatch to the GPU 8 times, basically dispatching to the GPU takes a large amount of time, transferring memory over, etc. Giving the instruction takes time. So you'll be waiting a huge amount of time to do this. But if you combine all of them together and you have one thing of size 128 and you dispatch only one time, the actual doing the addition will take the same amount of time. It will literally take the same amount of time. So you'll just be 8 times faster if you do that. Even for things like matrix multiplies, which take a certain amount of time, matrix multiplies are really, really fast on GPUs. So this is essential. Even on CPUs, have people heard of SIMD instructions? So SIMD instructions are single instruction, multiple data. So basically adding together 16 floats is as fast as adding one float in many cases, if you use the appropriate instruction set and everything. So even on CPU, it's very, very useful to combine together things into larger things. So this is an illustration of what we do. So basically, we take together 3 examples of a hidden layer in a neural network, where each one has its own X. And what we do is we concatenate these together into one matrix. And we do a single matrix multiply instead of 3. So this is 3 times faster on our GPU, basically, if it's a small enough matrix multiply. then this B thing here, we have to do something called broadcasting, where basically we don't actually make 3 copies of it and put it into columns, but we pretend like we did. And then if we do this, we can basically do this operation 3 times faster than we would do normally. So the way you can do this in a model by hand is basically you group together similar operations, loss calculations for a single word, and execute them all together. And in the case of a feed-forward language model, each word prediction in a sentence or across multiple sentences can be batched together, because they all kind of have the same shape of taking the 2 previous words and predicting the next one. For recurrent neural nets, this is more complicated, and we'll probably talk about this in the recurrent neural network section. Dynet has special mini-batch operations for lookup and loss functions. Everything else in the middle is exactly the same as if you weren't doing mini-batching. So kind of what it looks like here is we have this, where we would be doing a lookup at the beginning. This is basically our feed-forward language model example. We would be doing lookup of the previous word and lookup of the next word here. And what we do instead is we take in a vector where we have basically a set of tuples where each represents one of the words. And we call this lookup batch function. Then the thing in the middle is exactly the same. Then when we calculate the loss function, we also calculate the loss over multiple output instances. And there's an example of this in the code as well. In the code examples as well, and you can see basically what we're doing is passing stuff in there. I can show that at the end of class if people are interested in looking at it, but we only have 5 minutes, so I won't do that now. You can try running the batched versus unbatched example, and you can see it's probably about 3 times faster on this CPU, and it's probably quite a bit faster than that on the GPU. So the final thing is Dynet and also TensorFlow Fold is another example. I have a thing called automatic mini batching. TensorFlow Fold is automatic mini batching in a static framework, so you have to kind of learn a special language to do it. Dynet, basically what you do is you calculate the loss function for example, 3 sequences at once. You add them together, and then you turn on a command line flag, and it automatically does this for you. So it's pretty easy to use. We have a nice GIF that Yoav Goldberg made for us. So let's see if it runs. Oh, this is a PDF, which cannot run GIFs. So, that's annoying. Hang on 1 second as I pull up the slides in Keynote. So anyway, the idea basically is that where normally we go in and try to find things to mini batch together on our own, the engine can actually do it for us. It can go in and search for things on our search for places where it can batch things together. And here. So we have these 3 things of a length, and we can run through, and we combine their losses together by just adding them together. And then the auto batching engine, it goes and finds operations that can be done together. So these operations can be done together, and then it executes them, and then it steps through and finds things that can be executed together, like this, and does this for you, essentially. So this is a little bit, so let me go back. Let me go back to the PDF version. And It's a little bit faster than if you do it, or a little bit slower than if you do it yourself. So sorry, here's the workflow. So for each data point that you want to do this for, you add the data and then you sum the losses. And the forward, you do the forward pass where the auto batch engine does magic for you, and then backward and then update. And we have some results for this where basically it's a bit slower than doing it on your own in kind of the ideal scenario. Because humans are smart, we can go in and do things. Efficiently, but it does pretty well. It still gets a factor of 10 increase over not doing batching at all. And the more important thing is it's also very easy to use in things where batching is difficult, like if you want to do a BioLSTM tagger with character embeddings added, or a tree LSTM or transition-based parsing, which are some of the things that we're going to cover later. So if you want to do manual mini batching, you'll get the best speed out of that, but this is also an option if you don't want to go through the trouble for the particular model you're using. So yeah, that's all I have for today, and we have 1 minute till the end of class if there's any questions. Yeah.
In my experience, the batch size has an effect on the,
Uh-huh.
the actual outcome of the.
Yes, yeah.
But so, like theoretically, a bigger batch is better because it's more stable. The gradient is more stable.
Yeah.
But some papers show that if you increase the batch to a certain number, then it becomes worse.
Right. So there's two trade-offs. One is that it is definitely more stable if you have a larger batch, but it's also easier to fall into local minima or local optima. So stochastic gradient methods actually can jump out of local optima, which makes them get better results sometimes. So, yeah.
Is there a deterministic algorithm to come up with the optimal mini batching scheme?
So the question was, is there a deterministic algorithm to come up with the optimal mini batching scheme? Yes, but it's NP hard. Yeah. Okay, I won't keep people over time, but thank you, and I will see you next Tuesday. Next Tuesday we will be talking about word embeddings. Yeah.